Can you hear it? Okay, okay. So we're going to talk about today about the platform root of trust module and why you are proposing a standard architecture for that. And then so this one is myself, Lawrence from Intel, and Lucy from Intel. We work together defining a standard architecture for PFR. As you know, the PFR is so far still in the DCSCM and DCS-MHS module. PFR is non-standard, it's an optional item. And we're hoping to propose that as a standard item in the PFR. So Lawrence and Lucy, they're unable to attend today, but I'm just going to talk for them. So from the agenda perspective, the need for a so before we go, need for a unified standard PRoT module, we're going to define what is the system architecture, and we're looking at the whole industry. It's not only PFR, but you have other security components in the system like TPM, TPCM, and the PFR obviously, and the combination of all this together. So we're going to look at that. So we're going to try to define a standard hardware interface. And then some of the use cases that we're going to talk about, it's a very simple, the way that architecture is defined, it can cover pretty much all the use cases that we see today. And then we also have, we want to take one more level up to have the PFR also as a root of trust for a platform as a root of trust hub. So we're going to talk about that today, and definitely last is call of action. So before I go there, I think the PFR, I just need to define a little bit of the PFR, right? So PFR, by definition, is platform firmware resiliency, which is defined by NIST. NIST basically gave a compliance spec, and Intel had provided an implementation spec. Why need a PFR when you have TPM and all those things? Because if you look at really TPM, what TPM does is a boot time protection, right? But PFR is actually T-1 protection. So PFR actually verifies the boot firmware, which is BIOS firmware, and also the BMC firmware. Now, if you have no way to turn up the system, if you have the corrupted firmware, the only way to turn up the system is to load the corrupted firmware. And by the way, BMC is outside of the power sequencing hallway. So BMC is always powered up. So you want this protection at the T-1 first, and also in case if anything happens, any kind of hacking happens, you want to be still boot up with a golden known image that is known, and then get an alert or CPU alert that yes, something bad happened, and you can take care of that, right? So that need is very, very real, because there is no other way to boot up the system if you have BIOS and BMC firmware hacked somehow, right? So that's a PFR. So problem is that we see a lot of cases where PFR is designed in a very different ways. We don't have a standard definition yet, and that's what we are trying to do here. And obviously, as you see the more and more CPU generation comes, we see different boards design, different PFR design. So our goal is to construct an architecture that accommodates multiple types of security that we see. That could be PFR, that could be TPM, that could be TPCM and those things. So benefit is obviously the product feature will have the flexibility. There is multiple organization who is defining the security, TCG, CNSA, NIST. So we are trying to put together all of we looked at all of those things, and we're trying to propose a standard architecture. So let me go to the next slide. So this is the PFR subsystem, and you can see that there's a T-1 mode, which is basically pre-boot mode. So basically, before you boot up the CPU with the BIOS and BMC with their firmware, you want to make sure that the T-1, those firmwares are authentic. And if they are not authentic, then you want to make sure that you have a way to boot up the system still and do the debug of the system. So that's where the T-1 protections come in, where you actually can boot up to a golden image in case if it's hacked. But this is just not in the T-1, but even in the T0 mode, that means when you're running, and if someone wants to hack the firmware, if someone wants to make sure, if you have the CPU image stored in a flash or BIOS or BMC image stored in the flash, and someone wants to hack that flash, do something bad with the flash, like chip erase command or writing somewhere they're not supposed to write, that's the T0 mode that we want protections, right? So by the way, we want to take the PFR a little bit above level because even though I'm saying it's a CPU and BIOS by definition of this NIST compliance, but it is any privileged firmware that can protect, right? By the way, the BMC and BIOS is the most privileged firmware in any server because they can see all the passwords, all the keys, and all those things. So that is highly privileged. So that's the reason BMC's BIOS comes into play. Anyway, so key architecture, you can see the key components there is the PRoT chip. We have some platform CPLD, which does the power sequencing. We have BMC, obviously. And then you have BIOS flash, BIOS to the SPI flash, BMC attached to the SPI flash. And then the SPI box logic is basically make sure who takes the control of that bus, right? In case if something bad is happening on the bus, someone is trying to hack on the bus, you want to make sure that the root of trust get control of the box logic. And then obviously, you also want to have PSU firmware and all this firmware verification. It's just a subsystem that you can add. But that's what they're defining, and then definitely you can see all the numbers there. So we also try to define the PFR module as a mechanical form factor because you see different connectors. If you look at Intel reference architecture, Lincoln City has one custom connectors. You can see Avenue City has a different connectors there. Obviously, if you look at Flex and other guys, they're doing something, again, they're custom design. So there is a lot more connector design, which is one of the way it's bad for the industry to actually standardize everything. So we are proposing a M.2 mechanical form factor. So M.2 is very standard now. Everybody knows it is. Everybody uses it. M.2 has about 67 pins that you can go, and we can define the standard PFR architecture with 66 pins. So, and since M.2 is the most widely used today, we're just proposing that, hey, we can use the M.2 form factor for this standard PFR TPM, TPCM module. And then obviously there is some height requirements. You can see that we're defining this mechanical form factor, size, and all those things. So this is how we are defining the pin definition of the PFR module. So as I said, this M.2 has 67 pins, and we're defining these 66 pins there that can use a standard PRoT module. And again, as I said, it's a platform root of trust. It could be TPM, it could be TPCM, it could be PFR. But this is how we are defining those things. And all the pins, that architecture that we see today can actually fit in this architecture, this pin definition that we had. It's probably difficult to go line by line for all the pin definition because I only have 5 minutes left. But you can see that this is what we have, and definitely the presentation is available after this today, and we can definitely argue that. I'm going to propose this also we're going to propose this to OCP as well to make it a standard, but this is what the key things here, how we are defining the pin. But the main thing is that we're not defining something new. We're defining, staying within an M.2 form factors. And M.2 pin definition is very standard. The storage guys, server guys, compute guys, edge guys, everybody is using M.2 today. So this is kind of like fit very nicely. M.2 has 67 pins. We need 66 pins, so it fits properly. So there is the few use cases that I just want to talk about, just to show that how simple it is. Because in the PRoT module, so if you look on the left side, we're defining, so architecture is still the same. It is how you enable those SPI muxes and flashes are different based on different application. So your hardware architecture is very similar. It's a firmware tweak that needs to be done. So if you want to play as a PFR plus TPM, so I'm going to define a little bit about what is TPM does, why PFR is needed, right? So PFR, as I said, is a T-1 capability. TPM is not T-1. TPM does, during the boot up time, TPM does measurement of the various system components, right? And that's how it verifies. But even before TPM, you still have BMC that's booted up already. You still have other things that you need to make sure. So that's what PFR does. So PFR plus TPM, kind of like T-1, T0, you can use it. And there's nothing different about TPM that cannot be implemented in the PFR. But obviously, TPM has a lot more compliances. So that's what we're trying to integrate PFR plus TPM inside one architecture. And obviously, you can use the same thing as a TPM. Again, there's no differences there. The architecture is still, architecture that we're proposing is same. Hardware architecture is same, and that's how we are trying to get more industry involvement here. Only thing you're doing is how we're switching muxes and flux, muxes and switches. That's what we're doing. So if you go to the next one is TPCM. So I just want to talk about a little bit about TPCM. We know TPM does is basically the measurement of the platform components. TPCM takes one more above level. It actually looks at platform operating system, PXE boot, and all those things, and it does the measurement of those things. That's to make sure that because TPM doesn't do operating system, so that's to make sure the operating system, PXE boot, all these things, and if you have any additional requirements, you can put it in the TPCM. So TPCM is Trusted Platform Control Module that takes care of the TPM plus both. But in the TPCM mode, you can see that we're setting up this muxes in the bypass mode because you're not really getting this continuous protection of the BIOS and BMC flash in the TPCM mode, which is PFR does. PFR actually snoops on the BMC and BIOS image, and then basically tries to protect access or tries to go bit by bit protection anybody who tries to hack. So this is a different module, different way of doing it, but architecturally it's still the same. So that's what we're trying to propose, a standard architecture, right? And then obviously on the right side, you have TPM. Again, is a very similar. TPM has a less functionality than TPCM. So TPM does pretty much what, again, this is minus PFR. So if we go to the next slide. So next slide, I'm just taking a little bit above level about, so we talked about PFR, we talked about TPM, we talked about TPCM, we talked about all, various other things, and I have only five minutes only. So, but we want to show also that the platform root of trust can also do the attestation, because attestation is something that in a system level, if you look at, it's not only the BIOS firmware, not BMC firmware operating system, you still have so many components there that needs to verify who are there, right? That's the attestation part of it. And so attestation, you can also use the PFR as an attestation device for CPU or any peripherals. By the way, PFR or platform root of trust, this supports the MCTP protocols. And that's the standard protocol, and that's the standard that we are proposing too. That PFR should support a standard I2C that can support MCTP and that can actually do SPDM running over MCTP, and that's what you're doing here. So it can work as a device root of trust as well. And the last one, I think I don't have too many slides. I do have. So this is the one that I just want to talk about a little bit. I think this is one of my favorite subjects because, so the PFR today is already defined. We have, TPM is defined. But one of the biggest problems that we see challenges in the industry today is that when you talk about attestation, there is so many devices in a system that needs attestation, right? You have CPU, you have storage, you have memory cards, you have NIC cards, you have power supply, you have fans. There's so many things that needs to be attested today. And BMC does a very good job doing that. BMC does attestation. It's a convenience. It's not that BMC is a root of trust by definition. BMC is a system management chip. But it's a convenience for BMC because BMC has a pipeline or hook to all the system peripherals inside the system. So the way you can do the platform root of trust by BMC is the BMC can talk to the SIM, so why don't you make BMC as a root of trust hub, which is what people do today. As I'm saying, it's a part of the convenience. It's not a security, it's a flaw, security flaw, I would say that. And because of the convenience, people do that, right? Because BMC talks to all of them. Now, if I want to design a platform root of trust that can talk to all the peripherals, that's a major change in the motherboard, right? Because you're talking about pipelines or traces going to all your 30 or 40 peripherals that you have, and it's a significant changes in the motherboard design. So the one we proposed here is that, hey, you know what? We can still use the existing pipeline that BMC use, right? And then step behind BMC, because we talk to the BMC, and just kind of like use the BMC as a bridge, and then do that attestation on us, but BMC will pass the command to us. So BMC is going to be transparent. It's just going to pass through, so back and forth, all the commands that we have, and that's what we are proposing. So with that, I have call to actions. So the call to actions is obviously we are proposing a standard today. PRoT, platform root of trust attestation. Things are not standard yet. So we're proposing a standard architecture. So we'd love to get support from you guys. We're going to take this to the OCP standard committee, and this is the first step that we are doing it. And then obviously I'll definitely seek any feedback from anyone that will be part of these things. And then just to look at, you can look at the Calyptra spec in this internet. Calyptra is a self-attestation. It's different than platform root of trust. So you need to understand that the difference is Calyptra is satisfying its attesting itself, but it's not doing any root of trust hub that can have the overview of the whole platform, right? And then we have Intel PFR spec. Please take a look at that, which defines the implementation. And then there's some hardwares, white papers that we wrote. With that, I think I have still 2 minutes. Any questions or anything from anybody?
Yeah, I had one. The pinouts on your use of the M2 connector, are those the standard M.2 pinouts, or the specific?
Hardware is standard, yes.
Okay.
Standard pinout, yeah. We are defining the signals through the pinout.
Very good. So they could plug in, the unit
Right.
could plug into any M.2 connector.
M.2, yes.
Thanks.
Hello, I have a question. So the PFR is designed as a module. So can I just design a fake module and then to bypass all the security check?
No, because there is some I2C communication that you can see the handshaking between the BMC that we have defined here. So you can actually do some, some handshaking, key exchange. You can do that. You can also have a PFR presence, signal that can be authenticated by anyone, by entity. So you can actually do that. You're right. You can do that, if you were, but we have some check there.
Okay, thank you.
John Gelderman, Gyoxia. I'm on that PCI committee. You don't get to change the signals. We'll be happy to give you a new key, but you can't make something which is not interoperable into somebody else's standard.
Okay.
No, you don't get to redefine the signals.
Yeah, I understand. Yeah, thank you for the feedback. But yeah, we need to work together, definitely, how we can do it. Yeah. This is just in a proposal, yes.
We have, someone else did that in the past and it created a fire damage issue.
That's good feedback.
It's not good.
Okay.
So happy to give you a new key.
Okay.
Really happy to.
So we'll definitely, I'll talk to you, thank you. Thank you for that. Yeah, we're just looking for feedback. I think this is a very important feedback that we don't want to touch the PCI spec, obviously, but we're going to stay within the same. I think the physical, all we're looking at is the physical interface, just the hardware itself, so that people can buy the component. That's what we're looking for. Thank you. Okay, if no more question, I'll be here in the floor. So please feel free to ping me. With that, I conclude. Thank you, guys. Thank you.